The empire of classical computing has begun to fracture. For decades, the binary laws of 0 and 1 have ruled our world, but they have finally hit a wall. In October 2019, a single paper published in Nature sent a shockwave through global intelligence agencies and tech titans. The title? Quantum Supremacy. Behind this clinical term lay a terrifying reality. The world's most powerful classical supercomputer, Summit, would need 10,000 years of continuous calculation to solve one specific complex problem. In a secret laboratory in Santa Barbara, Google's quantum processor, Sycamore, completed it in exactly 200 seconds.
And a quantum computer is fundamentally different.
By compressing 10 millennia into 3 minutes and 20 seconds, humanity witnessed the first true defeat of the binary age. This is more than a technical leap. It is the beginning of the end for the digital civilization as we know it. But the old guard did not go quietly. IBM, the architect of modern computing, immediately struck back, claiming the task could be done in days, not millennia. But they missed the point. It wasn't about the specific number. It was about the shattering of the limit. This was the moment a 40-year-old prophecy by Richard Feynman became flesh. To understand this revolution, we must look at the fundamental unit of computation. Classical computers use bits, like a light bulb that is strictly either on or off, 0 or 1. Quantum computers use qubits. By harnessing the divine laws of quantum mechanics, qubits can exist in a state called superposition, acting as both 0 and 1 simultaneously. Imagine a spinning coin that embodies both heads and tails at the same time. But it doesn't stop there. Qubits leverage entanglement, a phenomenon Einstein called spooky action at a distance, where the state of one qubit instantly correlates with another. They also use interference, acting like ocean waves that can amplify correct solutions while canceling out incorrect ones. To control this delicate state, Google created the coldest spot in the known universe, colder than deep space, cooling the superconducting circuits to minus 273 degrees Celsius. In that absolute silence, qubits explore trillions of mathematical pathways at once, processing information in parallel while the classical world crawls line by line. Despite the miracle of 200 seconds, we are still in what scientists call the NISQ era, the noisy intermediate-scale quantum era. Today's machines have on the order of 100 qubits. They are powerful enough to study exotic matter and make breakthroughs in physics, but they have a fatal flaw. They are incredibly fragile. Qubits are susceptible to temperature, vibration, and even stray particles of light, which cause them to lose their quantum information. A problem known as decoherence. In classical computing, an error happens perhaps once in a trillion operations. In today's best quantum computers, an error occurs roughly once in every 10,000 operations. To achieve true quantum supremacy and build a fault-tolerant system, we must bridge this gap. The answer lies in quantum error correction. This is a software and hardware technique that encodes the information of a single qubit into multiple physical qubits, creating one stable logical qubit. The ultimate goal is to build a machine with millions of physical qubits. Scaling from 100 qubits to millions, with individual wires for each, massive dilution refrigerators, and complex chip architectures, is the most monumental engineering challenge of our time. For those holding stakes in silicon and software, the message is clear. The hardware race has a new king, but the marathon has just begun. Why are superpowers and tech giants pouring billions into a machine so difficult to build? Because greater processing power doesn't just make things faster, it enables entirely new applications. Quantum computers will allow us to directly simulate the fundamental processes in nature. Consider global fertilizer production. The current method, the Haber-Bosch process, consumes a staggering 2% of the entire world's energy. Classical computers cannot simulate the complex underlying chemistry to find a better way. Future quantum computers could model these chemical processes with unprecedented accuracy, potentially revolutionizing global energy consumption. From designing the perfect lithium-ion batteries to simulating fusion reactor dynamics, the economic potential is astronomical. But this incredible power casts a dark, terrifying shadow. If 200 seconds can bridge 10,000 years, what happens when this miracle is applied to the walls protecting our world? Since 1994, we have known about Shor's algorithm, which theorized that a reliable quantum computer could efficiently break the public key encryption, like RSA, that guards our national secrets, bank accounts, and blockchains. That encryption is built on the assumption that 10,000 years is an eternity. Quantum supremacy has proven that eternity can now be bought for 200 seconds. While we are still millions of physical qubits away from breaking RSA, the threat is already here. Adversaries are executing store now, decrypt later attacks, harvesting encrypted data today, waiting for the day a fault-tolerant quantum computer comes online to unlock it all. In response, agencies like NIST have released post-quantum cryptography standards to secure our future. The transition must begin now. The shield is breaking. The era of binary certainty is over. We are stepping into a probabilistic future where the impossible becomes instantaneous. Next time, we witness the fall of the digital fortress.